All right, in the last video, we looked at the relative sizes of atoms. In this one, we're going to look at something called ionization energy. It's essentially the energy required to remove an electron to form an ion. So technically, we're removing an electron from its ground state, whatever the lowest state it can be in. Technically, in the gaseous form, it's actually harder in solids and liquids, but the main thing I need you to know is it's the energy required to remove an electron from an atom. Okay. Just glancing at this, removing an electron is going to make things positive. Well, we know from like when we learned how to name things and we learned what charges are, that things over here like to have positive charges and things over here like to have negative charges. So it's probably going to be easier over here and harder over here. Okay? It's not always that easy, but we still need to look at the concept here. The trend is not as set in stone as we saw on the last stuff. Okay? So I'm actually going to look at like a specific example and kind of look for trends in the data. So we're going to look at boron. We're looking at element 5. So we're only worrying about 5 electrons. And I'm going to draw the orbital diagram just so you can see all the boxes and arrows, every single electron. So it's 1s2, 2s2, 2p1. Okay, so what we are going to do is we're going to look at how much energy it takes to rip off each of these individual electrons. So if we take boron and we rip off 1 electron, we get boron with a plus charge, and an electron as a product. It gets removed, whatever. This is known as the first ionization energy. It's the energy to rip off the first electron. And for I1, this is the electron being ripped off, whatever the last one was that was added. Okay? And its value is 801 kilojoules per mole. We have no perspective at this point to know whether that is a big number or a small number. That's okay. But what it tells us is that this first electron, this 2p1 electron, is going to take 801 kilojoules if you had a mole of boron atoms. Okay? Well, to rip off the next electron, we're essentially starting with B plus because it already has a +1 charge, and we're ripping off yet another electron. This is the second ionization energy. This number is 2427 kilojoules per mole. So the first trend that we're going to notice as this goes along is that it gets progressively harder to keep ripping off electrons. The first one's pretty easy, and then this number is going to keep going up for each ionization. Okay? This was the first ionization energy, was ripping off that electron. The second is this one. This is going to be the third one. But we're already at a 2+ because we've already ripped off 2 electrons. Going to a B3, from 2+ to 3+. This would be I3, the third ionization energy, because the third electron being ripped off. Its value is 3660. Okay? Now we've ripped off 1, 2, 3. Now we're going to rip off this one. Oops, 4+, and an electron. Okay, I4, the fourth ionization energy, is 25,025. All right, so we saw a huge jump here. I'll explain why in a minute. Okay, now we're ripping off the last electron. So we're starting with a B4+ charge, and we're forming B5+, which is essentially just a boron with no electrons at all. And I5 for that is 32,822. Okay, so here's what I'm going to tell you. I in no way, shape, or form need you to learn these numbers. We're just looking for trends. Okay? What we're going to see is that a lot of those trends actually sync up with some of the things we saw in the last chapter, where full orbitals are better than half-filled, which are better than partially filled. And core electrons, which we kind of talked about in the last video, are actually harder to rip off still. So what we see is that this first electron is a partially filled electron. I guess I'll try to label these. Which means it's reasonably unstable, and that's going to be I1, which is why it has the lowest value of the bunch. Okay. To rip off the second electron, this one would be gone, and you would now be disrupting a full s orbital. Okay. So for this one, you're basically ripping off a full s orbital. You'll notice that the jump from I1 to I2 is almost like 1600, a little more than 1600 actually, but the jump from I2 to I3 is like 1200. So the first trend we're seeing is these keep getting bigger, but the amount that it gets bigger, it actually is a bigger jump from ripping off the first one to the second than it is from ripping off the second to the third. This one, you're basically, it only has a half full s orbital, which means it's actually pretty easy to rip apart. Okay, really not a big deal. It's not as big of a deal as this one. Yes, it takes more energy because you're ripping negative things off of something positive, and negative is attracted to positive, so the more positive this gets, the harder it's going to be to rip electrons off, which we see this number keeps going up. But the difference is not very big here. Okay, I4, we have ripped off all of those, and all we have left is this. These are core electrons. This could be abbreviated as a helium. Core electrons do not come apart. They do not come off. They do not form charges. Now, the reason we're seeing it jump from, went from 800 to 2400 to 3600, now all of a sudden it jumped up to 25,000. This is the line in the sand. These are now core electrons, which is why it takes so much energy to rip these off. And you'll notice the jump here is significantly bigger than the jump here because you had a full s orbital here and a partially filled s orbital here, or a half filled, I guess. But it's still going to keep going up because you keep ripping electrons off of more and more positive things. So some of the trends so far is that every time you rip off an electron, the number is going to get higher. Anytime you have to mess with full orbitals or half-filled orbitals, you're going to see a spike in the energy. Okay. I want to look at one more set of data, one more trend, and see what we can spot here. Okay. So the general trend is that ionization energy increases to the right and up. So let's go with first ionization energy. Oops. First ionization energy, I1 basically, increases up and right on the periodic table, mostly. We're going to find that there are weird little exceptions and hiccups to the rules on these ones, but that's okay. We'll figure it out. Okay? So, let's look at some data here. What we're going to do is we're going to look at the entire second row, lithium through neon. And we're going to look at the first and second ionization energy to see if we can spot some trends here. I'm not going to do all the orbital diagrams and write out every single electron being ripped off. We're just going to look at I1 and I2. Okay, so it's still a table of data. I did not make any of these numbers up. You do not have to memorize the numbers. We're just looking for trends. Okay, so we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, we're going to be looking at I1 and I2, and these values are going to be in kilojoules per mole. I'm going to try to make a little grid here. Kind of sloppy, but it'll do. Okay, so I'm just going to write down the values and then we'll look for trends. So 520, 900, 801, which we saw earlier. Carbon is 1086. Nitrogen is 1402. This is 1314, 1681, and 2081. Okay, let's worry about this trend first. So we said that these things increase as you go up and right. This is left to right on the periodic table. Okay, element 3, 4, 5, 6, 7, 8, 9, 10. Okay, and for the most part, they do go up. Okay, This one has the lowest value, which makes perfect sense. We would have predicted that lithium's happy to form a +1 charge anyway. No matter what, it takes some energy to rip an electron off, but lithium wants a plus charge, so it's happy to get rid of it, okay? And then it goes up, which we expect, but then it actually drops back down. It's because beryllium has a full s orbital. Okay, kind of like here, like when we saw this big spike after the first one, this number got a bigger spike because we started hitting that full s orbital. Beryllium is starting with that. So essentially, the trend is going up, but we're seeing a hiccup here where it actually goes up and then drops back down because of a full s orbital. We actually see the similar trend here. This is going up, going up, going up, and then it drops back down because this is a half-filled p orbital. So that orbital stability stuff is kind of important. Okay. And then it keeps going up and up and up, and it makes sense that neon would be the biggest. It's a noble gas. It's happy to have all of its, basically it has all of its orbitals full. This is why the noble gases are happy. This has a full p orbital. Okay, so the trend mostly goes up as you go to the right, but this explains why there's weird little glitches in the number. So if I asked you, like, which atom would you expect to have a higher first ionization energy, nitrogen or oxygen? You would expect it to be nitrogen, even though the trend says mostly to the right. And if you drew like the orbital diagrams, you could see like nitrogen would have 3 up arrows, which would be half filled. Oxygen would have 1 extra, which would be that partially category. Okay. Let's look at I2. The trend we saw up here is that when you go from I1 to I2, the numbers jump. So all of these numbers should be bigger than their relative I1 values. So this value is 7,298. This is 1757, 2427. We saw that one earlier, right there. Carbon is 2352, and 2856, 3388, 3374, and 3952. So our trend was for first ionization energy. We're looking at the second, but there should be similar trends. First things first, this one is, lithium is actually the biggest second ionization energy of the entire second row. It's because the first one is really small because it was happy to move from lithium down to being like helium. That's what happens if it gets a +1 charge. But now you're messing with core electrons, okay? So this is the biggest of the bunch because these are core electrons, and messing those up is a notable problem. Okay. After you ripped off the first electron of boron, kind of like we saw up here, now you're messing up a full, the second electron would be messing up a full s orbital. Which is why we see this spike and then it drops back down. Okay, based off the trend between here, 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 and here, you would expect this number to be like, I don't know, around 2,000. But the fact that it's like 400 higher than that is because it's a full s orbital. Okay, if we keep going up, we see a spike and then a drop again. This is because oxygen was happy to get rid of its first one, but after you remove the first one, now it is left with a half-filled p orbital. Neon isn't going to gain anything new from this, it's just following the trend. After its full orbital's been messed up, it doesn't really care at that point. Okay, so if you're doing one of these problems, yes, the trend is that increases up and right, but you have to be aware of like full orbitals and half-filled orbitals and how that's going to affect things. All right, thanks.